Hello everyone, my name is Shyam Chauhan and today we are going to cover Theorem 1.3 Root 2 is irrational. Let us cover in short the Theorem 1.2. Theorem 1.2 says that P is any prime number and A square are positive integers. If P divides A square, then P divides A. P is any prime number, A and A square are positive integers. If the statement is if P divides A square, then P divides A. If I take one small example, that is, if I take prime number as 3, positive integer A equals to 21, A square equals to 21 whole square. Prime factorization of A equals to 3 into 7. Prime factorization of A square, that is 3 into 7 whole square, that is equals to 3 square into 7 square. If I see the factor of A, it is 3 comma 7, and if I see the factor of A square, that is also 3 comma 7. Now P divides A square. We need to check, does P divides A square or not. That is, 21 square is 441. We will check if P divides A square or not. If P divides A square, in this case it is 21 whole square, that is 441. 3 divides 441, this means we can say 3 also divides A, that is 3 divides 21. Now let us cover theorem 1.3. The statement of theorem 1.3 is root 2 is irrational. To prove the statement, we will use the concept, that is assume statement is false, then try to prove that our assumption is false and hence the statement is true. We will be given with the statement. In this case, the statement is root 2 is irrational. We will assume that the statement is false. We will assume that root 2 is not irrational. Then we will try to prove that our assumption, that is root 2 is not irrational, is our assumption that is false, and hence the given statement is true, that is root 2 is irrational. So let us start our proof. Statement is root 2 is irrational. We will assume that root 2 is not irrational, or we can say root 2 is rational. If for any rational number a, number say x, we can represent x as a divided by b, where a and b are integers and b not equals to 0. In this case, we have assumed that root 2 is rational, so we can represent root 2 equals to p divided by q, where p and q are integers and q not equals to 0. Now suppose that the p and q has common factors, then we divide p and q by common factors and get root 2 equals to a divided by b, where a and b are co-prime. I have made a detailed video on co-prime numbers. You can see lecture number 6 in this playlist. Then we have a and b are integers and b is not equals to 0. Let us name this as equation number 1. Now I send b into numerator. I will get root 2 into b equals to a. Now squaring both sides, I will get root 2 into b whole square equals to a square. Now if I see here, 2 divides a square because a and b are co-prime. A and b does not have any common factor, but 2 divides a square, so 2 is one of the factor of a. Two is the factor of a square, so by the theorem we can say 2 is also the factor of a. So I can write a equals to 2 into c, where c is integer. Now if I put this into this equation, that is 2b square equals to a square to b square equals to a equals to 2 into c whole square. Because of 2, I will get 2b square equals to 2 square is 4 and c square. I will get b square equals to 2c square. If I see here that b and c are co-prime, but 2 is the factor of b square. 2 is factor of b square, and by theorem we can say that 2 is also the factor of b, but this contradicts our assumption that there is no common factor other than 1. So we can say 2 is factor of b and a, but this contradicts the fact that a and b does not have any common factor other than 1. So I can say that our assumption that is root 2 is rational is false, and the statement that is root 2 is irrational is true. In next lecture we will see example number 5. Thank you.